Question 21 says, a lead bullet strikes against a fixed steel plate with a velocity 100 meter per second. The impact is perfectly inelastic and the bullet shares 60% of the heat produced. The rise in the temperature of the bullet in degree C is. Okay, in this particular question, the kinetic energy of bullet is converting into heat. The collision is perfectly inelastic. That means all the kinetic energy is being lost and 60% of the heat produced is shared by the bullet. So what is the temperature rise in the bullet? Now let's see. The equation that we are going to use is Q, that means the total heat absorbed is equal to mc delta T, where delta T is the rise in temperature, the change in temperature. The value of Q is going to be equal to 0.6 into half mv square. So let's put the value. It is half m. M is the mass of the bullet and v square will be 10 to the power 4 SI units, because v, the velocity, is 100 meter per second, and this is equal to m into specific heat, whose value is given, into delta T. So the expression for delta T then is coming out to be 0.3, because 0.6 by 2 will be 0.3 into 10 to the power 4. M will get cancelled and the value of C is 125 joule per kg per Kelvin. So this is going to come in terms of Kelvin, and this value is 0.3 into 10,000 by 125. So 10,000 by 125 is 80, and 80 into 0.3 will be 24 Kelvin. So the rise in temperature of the bullet in degree C, well, if the rise is 24 Kelvin, then the rise in degrees Celsius is also 24 degrees C. So this is 24 degrees C. So answer to question 21 is 24. Let's go to the next question now. Question 22 says 1 mole of a monatomic ideal gas undergoes the cyclic process ABC as shown. BC is an isotherm at 800 Kelvin and the temperature at A is 400 Kelvin. If the heat absorbed by the gas in the process BC is P into 100 R ln P, then the value of P is. Okay, so the BC is an isothermal process, and we know that work done in isothermal expansion can be given as W is equal to nRT ln Vf by Vi, the final volume by initial volume, that is Vf, and by Vi. Now in this particular case N is 1 and the temperature is 800 Kelvin. So this is equal to 800 R into ln Vc by Vb. So now to find the work done, we have to evaluate Vc by Vb, and we can see that from the graph it's very clear that Vb and Va are equal, and we can easily relate Va and Vc by using the ideal gas equation. Now since temperature at A is 400 Kelvin, so that means pressure Pa and Pc, they are both equal. Let's say that pressure is P0. P0 into Va is 400 R by applying the ideal gas equation, and similarly P0 into Vc, the temperature there is 800 Kelvin, so it is 800 R, and we can see that Vc by Va is 2, and this is also equal to Vc by Vb, because Vb and Va are equal, and so the work done in the process BC is 800 R ln Vc by Vb is 2. So this is the work done. Now we have to compare it with P into 100 R ln P. Well, we can write this work done, W that we have. This can also be written as 8 into 100 R. Let's say it is 8 into 100 R ln 2. And that means we can further write it as, because we have to get the same number at these 2 points. So if I put it as 4 into 100 R ln 2 to the power 2, that means ln 4. We can write this work as this, and by comparing these two equations, we can see that the value of p is coming out to be 4. So that means our answer to question 22 will be 04. Let's now go to the next question. Question 23 says 1 mole of an ideal gas undergoes a cyclic process ABCA as shown. The maximum temperature attained during the cycle is n P naught V naught by 4R. The value of n is. It's very clear that the maximum temperature will be obtained somewhere on the line AB. Well, it's a PV graph, and if I draw an isotherm through point A and B, we can see that at A the product of pressure and volume is 4 P naught V naught, and at B also the product of pressure and volume is 4 P naught V naught. So that means TA equals TB. So one thing is that TA equals TB, temperature at A and B are equal, and isotherm through these 2 points should look like this, and which means that the temperature at other points on the line segment AB, other than A and B, points A and B, the temperature is going to be more than temperature at A and B. So to find the maximum temperature, let's write the equation of the straight line AB. An equation of the straight line AB can be written as P is equal to whatever its slope, let's say mv plus c. The slope itself is equal to, we can see that it is negative, and it is minus 3 P naught, that means 4 P naught minus P naught divided by 4 V naught by V naught, that means minus 3 P naught by 3 V naught, V plus C. So the equation turns out to be equal to minus P naught by V naught V plus C. And to find the value of C, let's put this point, which is V naught comma 4 P naught at point A. So at point A, if I put the coordinates, it is 4 P naught is equal to minus P naught by V naught into V naught, that means minus P naught plus C, and that tells that the value of C itself is 5 P naught. So the equation of the straight line then is equal to minus P naught by V naught V plus 5 P naught. Now since we are interested in finding the maximum temperature, we can use the ideal gas equation and bring in T here. So if I put PV is equal to RT, because it's a case of 1 mole, so P can be written as RT by V. So that means we have RT by V is equal to P naught by V naught V plus 5 P naught, and we can remove V from here. We can put it as square, and then one V will come here, and this R also we can remove from here. R will come here, and it will come here too. So this is the expression for T. There is a minus sign, of course. We can see that it's a case of inverted parabola, T versus V graph. It will have a maximum, and for maximum value of T, dt by dv has to be equal to 0. So if I put dt by dv equal to 0, we get minus P naught by R V naught into 2V plus 5 P naught by R is equal to 0. And this means that we can strike off all R, because on the right hand side is 0. The value of 5 P naught is equal to 2 P naught V by V naught, or V is equal to 5 V naught by 2. So if I put V is equal to 5 V naught by 2 in this equation, we shall get the maximum temperature. So T max will then be equal to minus P naught by R V naught into V square, and V square we have to take 5 V naught by 2 square, that means 25 by 4 V naught square, plus 5 P naught by R into 5 V naught by 2, and this we can see by solving that this will come out to be equal to, it's 25 P naught V naught by 2R minus 25 P naught V naught by 4R. This value is coming out to be 25 P naught V naught by 4R. Now if I compare it with this equation, we can see that the value of n is 25. So our answer to question 23 is 25. Let's go to the next question now. Question 24 says 1 mole of ideal argon gas is contained in a fully expandable balloon at 25 degrees C. Assume that the balloon requires no energy for its expansion. If the balloon is slowly supplied 125 joule of heat, then the final temperature of the gas in degrees C is, and the value of R is to be taken as 25 by 3 joule per mole per Kelvin. Well, we can see that no work is being done for expansion of the balloon as such. So we can consider the entire process to be isobaric process where the pressure is same as the atmospheric pressure. And if it's an isobaric expansion, then delta Q in fact is given to us. And so we have the equation we can write from the first law of thermodynamics, and considering that it's an isobaric expansion, delta Q is equal to NCP delta T. Well, the value of N is 1 and it's argon gas which is monatomic. So that means value of Cp is 5R by 2. So this is equal to 5R by 2 into delta T, and its value again is given as 125 joule as per the question. So the value of delta T, the change in temperature, is simply 125 into 2 divided by 5R, and the value of R is 25 by 3. So this is what it is. So this is the change in temperature in Kelvin, and this is also the change in temperature in degree C, because change in temperature in Kelvin and Celsius will be same. So let's simplify this. This is coming out to be 6 degrees C, and the initial temperature was 25 degrees C. That means the final temperature of the gas is 25 plus 6 or 31 degrees C. So 25 plus 6 is 31. This is the final temperature. So answer to question 24 is 31. Let's go to the last question of this test now. Question 25 says the ratio of work done by an ideal gas of rigid diatomic molecules to the change in its internal energy in an isobaric process is P by Q, where P and Q are co-prime. The value of P plus Q is. So it's given the ratio of work done by the ideal gas to the change in its internal energy is P by Q, and the process is given as isobaric process. We know that delta Q for this process is N Cp delta T, and which we can write as N into its diatomic molecule. So Cp for diatomic molecule is 7R by 2. So it is 7R by 2 delta T, and by first law of thermodynamics it is also equal to NCV delta T plus work done. So this is NCV delta T, and Cv is 5R by 2 delta T plus the work done, and this means that the work done is equal to N7R delta T by 2 minus N5R delta T by 2, and that means it is equal to NR delta T. That's the work done in the process. So the ratio of work done divided by delta U will be then NR delta T divided by N into 5R by 2 delta T. This is simply 2 by 5. Now question says we have to find ratio of work done by the ideal gas of rigid diatomic molecules to the change in its internal energy in an isobaric expansion is P by Q. That means 2 by 5 is equal to P by Q, and P, since P and Q are co-prime, so that means the value of P is 2, the value of Q is 5, and so the value of P plus Q is simply 7. So answer to question 25 is 07. Well students, with that we have come to the end of this discussion. I hope you found the solutions useful, helpful. Wish you all the very best. See you and take care.